Hello. Okay, so welcome everyone to the first day of Thematic program, Representation Theory, Vertex and Chiral Algebras. It's a pleasure to see so many people are able to come in person. This is also a hybrid event, so also welcome to people watching online. So I think what we're going to do is, for those who are watching online, you'll enter muted, but you're able to unmute yourselves. So if you have a question, please just ask, and we'll be able to hear you here. Otherwise, try to remain muted, please. For those who are here in person, if you have a question, please just try to grab our attention. We'll bring a microphone to you so that everyone's able to hear it. So I think that's all. Here's Wi-Fi access, and if you haven't registered yet, it's in room 208. So without further ado, it's my great pleasure to introduce our first speaker today, Terry Gannon, who's going to be talking about tensor categories and vertex operator algebras.
Thanks, and thanks for the invitation to be here. It's wonderful to be here for several reasons. One reason, this is my first visit to IMPA, to Rio, my first visit to Brazil, in fact, my first visit to South America. So this is really exciting for me. It's something I've wanted to do for a very long time. It's winter back home. We'll have snow on the ground for another 2 months. So it was quite a dramatic experience stepping off the plane in Sao Paulo. This is my first conference, and for many of you, it's probably the same, my first real conference since the pandemic. So it's the first time I'm speaking in front of people live in 2 years or so. So it's wonderful to be back at these kinds of things. And also, maybe even most significant of all, my job is to be head of my department, chair of my department. And so for all these pandemic years, that's all I've been doing is worrying about some professor complaining about possibilities of getting infected or whatever. Just endless stuff that I'm not trained to do, that I don't want to do, and that I've just quit doing. So as of July 1st, I'm no longer chair, but this is sort of my first taste of ordinary life. So for 2 weeks or so, I've told people mostly to ignore me, and I'm a researcher again for 2 weeks. So here we are. So we are staring at, there we are. So my talks are going to be on tensor categories and VOAs, but it's not going to be a series of talks on tensor categories. It's not going to be talks on VOAs. What it's going to be really is I'm going to try to indicate to you that if you're interested in stuff like VOAs, then whether you like it or not, you have to know tensor categories stuff. You have to use, at some point, very likely, some methods from tensor categories. And so the first talk is going to be, though, because it's a mixed audience, I imagine, the first talk will be fairly basic. So I'm going to mostly discuss an introduction to, a very brief introduction to the topics I'm going to be talking about. And so if you're interested in interesting things, then you're probably not going to be very satisfied with today's talk. And if you're interested in, if you're relatively inexperienced, then you probably won't like this talk either because it's going too fast. But that's what you do. You aim for the middle and you dissatisfy everyone. That's what being chair of a department is all about as well. So I'm good at that. Right, so our picture is the following. This is a picture that's superimposed on all of my talks, in fact, all of my work. So in principle, I'm interested in, usually, the top layer. So this is the source of 21st century mathematics. That's my interest in it. So CNF stands for conformal nets of factors. There's lots of mathematical interpretations of what a two-dimensional conformal field theory is. And so I just treat them all as one big blob. They all fit in the same basket, and you use whichever one is most convenient. So that's the purple level. That's the ultimate level that you're really interested in. But most of us very quickly move on. Those beasts are way too hairy at the top. So you simplify things down by shaving off the hair and projecting down to a very simple shadow. And so most of us, I think, who work in CFT, etc., really work in some shadow, combinatorial shadow of the upper layer. So things like modular data, fusion rules, that kind of stuff is some of the shadows that we'll be discussing in my talks here. But my point will be that to understand the purple layer, there are situations that I think are quite interesting where you really use an intermediate level, which is the tensor category world. So that's going to be the theme of my talk. But before we can get to the theme, we have to discuss a little bit what I mean by that green layer. So the starting point for this is representations of finite groups. Like, it's a starting point for almost everything in the world. And so these are finite groups over representations over the complex numbers, finite dimensional representations, the simplest thing that you can imagine in algebra, and it's the starting point, of course, for the whole story. I'm assuming that you all know this, so I'm going to go over this super quickly, but if I'm going over it too quickly, or I seem to have made a mistake, then just let me know. So a representation is, there's lots of different ways to think about the same thing. What we're going to do for concreteness is think of them as matrix representations. So to every element of your group, you have an n by n matrix for some n, and such that the multiplication in your group corresponds to multiplication of the matrices. And so here's a representation, the defining representation for the symmetric group S3. And so I wrote down there's 3 factorial elements of S3, so I've written down those 6 matrices. You all know, you've all seen this before, and so on the bottom there I have, I guess that's 1, 2, so it's 1, 2 composed with something else and equals something else. So this is an example of the group property, the homomorphism property of this representation. So we all know what group representations are all about. And so what are their properties? First of all, we have to have a notion of equality or equivalence of representations, and so that just means that up to a change of basis, the matrices agree. Another one is direct sum of representations. So that just means in this matrix language, you just put it into block form, block diagonal form. And so all this should be, I think, simple for all of you. And another thing, so one thing is we also have semi-simplicity. So there are irreducible reps you can't reduce as a direct sum of smaller things, and everything can be expressed uniquely up to equivalence as a direct sum of irreducibles. So the irreducibles for S3 are the sign representation, the trivial representation, and a two-dimensional representation, which I flashed on the previous slide but forgot to mention. We can also multiply representations. This is the Kronecker product. So what you do is you take, it's described here. If you don't know what it is, then tough luck. You don't really need to know. You can multiply representations, the tensor product of representations. It's just the natural representation of G on the tensor product of your 2 vector spaces, which comes from, it's just abstract nonsense. It just comes from it's the obvious representation you're gifted. If you're given a row and a row prime, the representation on the tensor product of those 2 vector spaces. Also, you have a dual representation. So given a representation on a vector space, there's an abstract nonsense way, one and only one obvious way, to write a representation on the dual space, the vector space of linear functionals. And so just, if you've never seen it before, I'm sure you all have. If you haven't, then just sit down with a blank sheet of paper, give yourself a minute, and you'll come up with this representation. And so in matrix language, you can write it like this, the transpose inverse of the other matrix. So using elementary properties of linear algebra, you know that this is also going to be a representation. Okay, so these are the super quick discussion of representations of finite groups. You all have seen this before. And so you can't actually write down these representations except in the most trivial cases. So, for example, the monster would require buckets and buckets of matrices of enormous size just to write down the smallest non-trivial representation. So you have to forget information, and that's usually what we do in mathematics. Mathematics is really the art of forgetting. And so there's some lazy things you can do about the representations, and there's motivations for this. So the basic combinatorics of it would be knowing the dimensions of representations, knowing what the duals are, and ultimately knowing how tensor product decomposes into a sum of irreducibles. And you can do all this. Okay, so here's an example for Sim3. There's 3 irreducibles, as we said before. They have dimensions 1, 1, 2. They're all self-dual, and you have these fusion rules, or these tensor product rules. Okay, who cares? So the point is that you can capture all that information much more elegantly in the character table, as you all know. And so there's motivation for defining the character table, but who cares for us right now? Because you've all seen it before, I'm sure. And so what you end up with the character table is a square of complex numbers. These are the size of the square is the number of irreducible reps, and which is also equal to the number of conjugacy classes, and you get a much simpler description of the representation theory of your group. So, for example, for the monster, you have your character table is 194 by 194. So you can write this down. In fact, it is written down. And so you don't have to write down this these 10 to the 54 matrices of size of 200,000-ish each. The character table is much smaller. But the problem, of course, is when you forget information, you lose information. And so you can ask, how much information do you lose? It's a bit of a subtle question to see what information about groups is captured by the character table. But anyways, it's very easy to see. Almost immediately, you see that you lose information. So for example, in the first time you have two non-abelian groups of the same order is in order 8. And there you have the dihedral group, the symmetries of the square, D4. And you have the quaternion group, so the group that comes from the obvious units of the quaternions. And they're very different groups. You can come up with your own reason why they're very different groups. But they have exactly the same character table.
So the character table is predominantly forgets a lot of information. You can't even distinguish two of the very simplest groups that we groups. And so, but these representation theories still knows the difference of these two groups. For example, so this is
Kind of embarrassing for people that love character tables, but if you take any representation of your group and you take its determinant, then you get another representation, a one-dimensional representation. The homomorphism property still works out. You get a one-by-one matrix representation of your group. And so we can take the two-dimensional representation for the dihedral group and take its determinant, and we'll get a non-trivial one-dimensional representation. We could take the two-dimensional representation of the quaternion groups. They both have a two-dimensional representation, as you can see in this lower corner here. You can take the determinant of the two-dimensional rep of the quaternions, you get the trivial rep. So this is a very elementary thing to do, but it already sees a difference between the quaternions and the dihedral groups, but the character table can't see that. So to get a full story of the representation theory of a finite group, you have to augment this combinatorial story slightly. So you have to unforget. You have to remember some things. And so there's different ways to do this. But the way that I think is the best way, at least to our current biases, is category theory. And so I know category theory, some of you are going to love it. In fact, you work in it. And some of you are going to hate it. And I am absolutely both. And that's okay. So certainly it's an abused notion, surely. But certainly there's also no question that it's extremely powerful. So the category of representations of your group any category has objects and morphisms. Here the objects are representations. Let's just take them for convenience and concreteness to be matrix representations of our finite group. And morphisms are called intertwiners. So these are matrices that that intertwine these two different representations. So for all little g, you have this identity here. So m is fixed. It's a constant. It's independent of g. And as you run over all g, that equation is satisfied. So these are called intertwiners, and they're the morphisms. And so I give a boring example here of two different objects in rep Z2. And of course, they're equivalent to each other because there's an intertwiner that is invertible between them. There's also non-invertible intertwiners, and an intertwiner certainly doesn't have to be invertible. In fact, you have a vector space of intertwiners. A more important example is for any group, any choice of representations, rho and rho prime. Rho tensor rho prime it's commutative up to equivalence. And so that means that there's some isomorphism that intertwines rho tensor rho prime and rho prime tensor rho. And so we're going to call this the braiding or abraiding. And so in particular, it sends the basis. So these are just the standard basis vectors of Cn. So it just sends them, it just flips them. So it's the obvious intertwiner, the obvious braiding. Okay. So that's rep G. And so it's a little bit more complicated than it looks. So just to help indicate what are some extra information here, so if the combinatorial side tells you if I have one of the irreducibles rho I, there's only finitely many of them, and I tensor it with any other one, then I want to decompose it into a sum of irreducibles. So those are the fusion rules, and as we know, it's usually good enough for most purposes. But in Rep G, the category, it requires knowing an explicit isomorphism between these. So, so that isomorphism is an invertible element in this Hom space, in this morphism. It's an intertwiner that maps here. So I'll tell you more about how big these intertwiner spaces are, but this is not a pleasant thing to do at all. So you don't want to roll up your sleeves and work with these categories, construct them from first principles. It's not a fun thing to do. Unfortunately, we're going to be doing some of that later. So the most important thing is that these things exist, and if you really, really, really need it, then you can go up to that level, but mostly you can just work with the combinatorial level. Okay, you'll see the blood and guts of these categories a little bit later, probably in the next lecture. Okay, so the essence of representation theory is category theory, I would suggest. So that's the lesson of finite group representation theory. It turns out that it completely characterizes the two groups. The combinatorial shadow, on the other hand, doesn't even distinguish D4 and the quaternions. So it captures everything, and it's a relatively gentle enhancement of the character table, which is very friendly from a functorial standpoint. And so representation theory, we should think of, is category theory, and anything else is a simplification thereof, probably. Okay, so this leads us to the notion of a fusion category. They're just that abstractification of Rep G, really. So they have direct sums, they have tensor products, and they have duals, and they're semi-simple with finitely many simple objects up to equivalence. And the Hom spaces are finite dimensional vector spaces over the complex numbers, and I think that's it. And so what we don't have in general is, for a fusion category, is that rho tensor rho prime is isomorphic, is equivalent to rho prime tensor rho. So we don't have this commutativity in general. When we do, more special things happen. So that's one distinguishing factor of Rep G from a generic fusion category. What I would like to do in the course of my lectures is try to explain to you how, fusion categories are a generalization of finite groups, and in fact, they're kind of the things that we can think of as acting on things like VOAs, on 21st century stuff. It isn't finite groups, it's fusion categories or stuff very closely related to fusion categories that do the acting. So we should think of fusion categories as the 21st century finite group. So the connection to VOAs, fusion categories, as I just said, play a role in the VOA story, as you'll see in my next lectures. But the actual category of representations of modules of a VOA is a fusion category, but it's much more. So we'll talk more about this, hopefully this lecture. Okay, so as always with categories, you can almost always forget that you're dealing with categories and project down to the shadow. That's almost always what people use. And so in the case of the fusion category, ultimately it comes down to what's called the fusion ring. So this is just up to equivalence how the tensor product of simples are. So these nijk's are non-negative integers, and they capture a lot of the categorical structure. In fact, there's a theorem called Ocnianu rigidity, which says that if you have two categories, so only finitely many different categories, I'll say what different means for these fusion categories, but only finitely different fusion categories can have the same fusion ring. So it's a nice theorem, but it's highly non-constructive. So finite numbers range from 0 to, infinity minus 1, I guess. So we could think of, one way to think about fusion categories is as a categorification of a ring. And so a categorification is probably a notion you've heard before. So in math, I said that math consists of forgetting information, but math also consists of enhancing information. So it's sort of the interplay between forgetting stuff and and enhancing. And so categorification is the enhancing process. So you add structure to it. So for example, if you have, so your set is replaced with a category, equality between elements in your set become an isomorphism between objects in the category. So for example, associativity, which we want for our tensor product in a fusion category to obey, we don't say that the tensor product of rho with rho prime with rho double prime equals rho tensor rho prime tensor rho double prime, or we add in brackets in a different order. We don't say that. Whenever objects are involved and you see an equal sign, you should be very nervous. You're not doing category theory anymore, probably. What you really mean is equivalent, and in a category theory, you want to then specify what that equivalence is. So when we say that our tensor product is associative, what we mean is, in the category theory, what we mean is we've selected some morphism. I think I have more on this on another slide. Yeah, I think I have more on this on another slide. What we'll do is I won't dwell on it right here, but we want to specify precisely which isomorphism are we talking about. And if we change this isomorphism, then in principle we could be changing the category. So that's part. So categorification looks at, it just lifts everything up one level. So you don't talk about equality of objects, you talk about equivalence of objects, which means you have to specify which morphism, which invertible morphism maps between the two. It has to exist, but it's not merely a case of existence. You have to point your finger at it. So function becomes functor, et cetera, et cetera. So you'll see more of this in the future slides. So the purpose for this is to increase the games that you can play. So we'll see examples of this. And maybe I'll say one simple example that means something to me personally. So in the good old days, so in 1978, a guy called John Mackay wrote Christmas cards to his various friends, some of whom were Fields medalists. And he just said, isn't it remarkable that 196,883 is pretty much 196,884. And that's all they did. He didn't explain it to these people. And so some of them, I'm sure, didn't know what he was talking about. But some of them knew what he was talking about. One of these numbers has to do with the number theory thing, the coefficient of the J function. And another one of these numbers has to do with the dimension of the smallest irreducible representation of the monster. And so one of the standard philosophies, strategies in categorification and in enhancing the structure is to replace a whole number with a vector space. Because you can do more with a vector space than you can do with a number. And so you replace 196,883 with a vector space of that dimension. And on that vector space, the monster acts. And you don't have to just look at the dimension of this vector space. You can look at the characters of this representation of the monster and ... You end up with moonshine, monstrous moonshine. So that's the strategy behind, that's one of the success stories of what you could call categorification or enhancing. There's lots and lots of success stories of it. Okay, so I should explain what I mean by some of the notions there. I'm going to focus on some of the notions and I'm going to ignore some of the notions. I'm going to focus on the ones that we'll actually need this lecture or one of the future lectures. So first of all, the notion of semi-simplicity. We know what this means in the rep G case, but what does it mean in a general categorical sense? Well, it's like everything, it's a bit complicated to spell out. And the only reason I'm spelling this out is not just to impress you with my knowledge, but that's part of it, of course, but also because we need this. So we'll need this in a little while. And so the idea is you just try to capture abstractly what's going on in a... I can make my slides available if people are interested in it later. But you just have embeddings and projections from your... So the picture is the picture that comes from rep G. So you're going to break you think of it as breaking your vector space up into the vector space V and the vector space V prime. Did I screw this up? I don't know what exactly I've been doing, V prime. Whatever, you get the idea. The first row in the first column is V. Second row, second column is V prime. And I'm going to get this backwards if I don't think carefully. So the primes, it looks like, are the... Yeah, so the primes project your big vector space into this small vector space V prime, or V, and the other ones are the transpose of those, the embeddings of this space here, V, inside the big space. The big space is V, direct sum V prime in rep G. And so you just combine projections and embeddings, and this is the formula that you get. And as I say, we're going to need this formula in a little while. That's why I'm writing it down. Okay, so we say that a category is semi-simple if, as is the case for rep G, there's a set of simple objects, xi, and we want there to only be finitely many of these up to equivalence, such that every object in the category is up to equivalence of finite direct sum of these simples. So that's what we mean by semi-simple. And so Schur's lemma tells us that your simple thing is that this holds in any fusion category. Your object is simple if and only if the dimension of its end space, so POM XX, is it's one-dimensional. So that means it's just multiples of the identity. What this implies is this bilinear formula. So the HOM space as a vector space is, you can easily see what its dimension is going to be, just by Schur's lemma. Okay, of course, just knowing that dimension, that's just the combinatorial side. You need to know often, at least on the categorical side, what else is going on. Okay, as I've said before, we're not requiring commutativity. So unlike rep G, we don't insist on our fusion categories to obey this commutativity formula. But the tensor product must be associative. And so as we know, instead of writing associativity the way that we would normally write it, instead we write it as, we have to spell out the isomorphism in particular. Now, what we know from our first course in group theory is if you have associativity, then in fact you get generalized associativity. So generalized associativity looks like, maybe I'll say rho tensor, rho prime, tensor, blah, 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 rho, lots of primes. And if I write them in exactly the same order, I get exactly the same thing. But to make this well-defined, I have to put brackets in, and I can do this in a random order. So let's say this way, and well, maybe this, and dot, dot, dot. This is a boring way to do it, and maybe a slightly more creative way. And then, I don't know, maybe this, and this, and this, and this, and however else. Anyway, you put your brackets, no matter how you put your brackets in a group, then you get equality again. So you just use associativity, just an induction, an unpleasant induction on associativity, and the base step is basic associativity, and then you get generalized associativity. And so the same thing will go in a fusion category. You'll get generalized associativity. But once again, we want a specific isomorphism. And so we want the isomorphism that you get by that proof of associativity. Let's do a concrete example. It can't be too complicated or I'll muck it up. This is kind of important, so actually, in a way, it's not important at all. But actually, it's kind of important. So let's do something. Maybe we'll do it in completely the reverse order. That's probably the worst case scenario. So we want to show that these two things work out. And so the way to go is from this thing, I want to use associativity. So associativity no longer exists. So associativity, so my alphas go from, so I have an alpha here that goes from rho prime, rho double prime, and I guess I want to tensor it with the identity on this thing, triple prime. This is going to move these brackets inside here. And I get rho tensor, rho prime, tensor rho double prime, tensor rho triple prime. And then what else do I want to do? Well, why don't I do alpha of row tensor, row comma, I guess. So this is going to be, the middle one is this one. So row prime tensor row double prime, comma, row triple prime. So I have all 4 rows there, but the middle ones are the tensor producted ones. So that's going to map this to row tensor. I'm not doing anything to the pair row prime, row double prime, so they stay as a tensor product. And now I'm tensoring row double prime. That. So I'm almost there. The final step then is this one. So the final step is to go, I do the identity on row. It's going to hang around for the ride. And then I'm going to get an alpha that's going to send me from row prime, row double prime, row triple prime. So I think I've done that right. So this is one path for going from here over to here. And so I get one expression. The composition of these alphas is going to be the one true isomorphism, the one true generalized associativity isomorphism between these two things. The unfortunate thing is this isn't the only path I could have done. So it's the only path I'm thinking of right now, but that's because of proximity to the blackboard. There's going to be, so I could have also done this, I could have kept these things together, and I could have moved this bracket to here, and then continued on in these lines. So, so there's another path. I could have gone from here to here, and I'll get a different combination of alphas in a different combination, and I get a different associativity isomorphism, and that's not a cool thing. What you want is there's one true way to do each one of these generalized associativities, and so the requirement is that for this one, these 2 different paths to go from here to here, these 2 different compositions of alphas have to be exactly the same. I think I wrote it down here. So you require a condition on, so there's the equation on the bottom there. That should be the correct expression for one path equaling the other path. So for morphisms, you can say that they're equal in a category, but for objects, you don't want to say that they're equal. You want to say they're isomorphic. And so in 2 categories, you also get nervous about saying that morphisms are equal. That makes me nervous whenever I say morphisms are equal, and so then you go one level up, but eventually you stop. At least ordinary people stop at some point. The only question is where you stop. Do you stop at the 0th step, or do you stop at the 1st step, or do you stop at the 2nd step? Okay, so really you have infinitely many different polynomial equations in the alphas that have to be satisfied, but there's a happy theorem that says that you just have to do one of them. So you need your basic data is the associativity here, the alphas, and then there's one relation that has to be satisfied, the pentagon identity that's written up there that comes from this isomorphism, this generalized associativity. All other generalized isomorphicities are fixed, are unique. All the other different paths, all other diagrams will commute. Okay? And this is going to persist on everything that you do for these tensor categories. You're going to I'm not going to go into the details for any of the other stuff, but you have basic data, and you'll have this, it's called coherence. You'll want to have unique paths between different things, unique isomorphisms between tensor products that should be equal. So that might involve commuting things or putting brackets in different places or whatever. And you'll require that all these different paths cohere, that they all give you the same. The diagrams commute. Okay. So that's this is part of the conditions on being a fusion category. Okay. Are there any questions on this? This is all. I think this is all pretty basic stuff, or should I speed it up? Okay. I'm not getting any much response, so I'll just assume that this is okay. You can always vote with your feet, right? If it's just too boring, then start leaving the room, and when enough of you leave, then when I notice, then I'll pick it up. Okay, so the babiest of all baby examples is vec, or vect. So the objects are finite dimensional vector spaces over the complex numbers. The morphisms are linear maps. So if you want, you can think of these as CMs and matrices, if you want. And so the unique simple object is, there's only one simple object here. It's the one-dimensional vector space, C. up to equivalence. And if V is n-dimensional, then up to equivalence, you can write it as C to the n copies of C, really n times C. And associativity here is the obvious thing, where you just don't write it like the way I did it there. So associativity should be the obvious associativity. You just change, I put my brackets on the second side wrongly. And the fusion ring, have I talked about the fusion ring yet? I'm not sure I talked about the fusion ring. I'm going to. Anyways, we'll talk about the fusion ring later. Another example is a slightly more interesting example, actually a much more interesting example, is vec G. So vec G is the category of G-graded vector spaces. All this has everything to do with VOAs, as you'll see later. So we're not, it might sound that we're far from VOA land, but we're there. We're just running around the edge of it. So G-graded vector space just means you can write your vector space as a direct sum of subspaces that are assigned the grading G, little g. Morphisms have to respect this grading. So your morphism is block diagonal in that sense. So you don't have a mix. Your morphism doesn't take you from a G-graded vector space to a G-graded space, a subspace that's given the grading of G, and another one subspace given the grading of H, unless H equals G. Anyways, it's written down there. And so you can see what it means to be isomorphic objects in this category. It just means that each of your graded pieces have to have the same dimension. So it's like lots of pieces of vec sort of glued together. I didn't explain. Okay, so that's what the objects and the morphisms look like, and it's a fusion category. That's right, because there's simples. So a one-dimensional vector space that's given the grading of G, little g, I mean. These are the simple objects, and then you can write any general vector space as up to equivalence. I'm being a bit sloppy there, as a sum of copies of these one-dimensionals. And then you can define tensor product explicitly by the maps I gave there. So it just multiplies these basis vectors in the obvious way. And dual is given by, I should have probably written that as CG, but the dual is given by just the inverse. The dual has the property that it's the unique. So given some simple object, the dual of your simple object is the unique object such that the tensor, so if this is your favorite object, and you want to know what the dual is the unique object up to equivalence, which has the property that this contains a copy of the tensor unit, a single copy of the tensor unit, and non-tensor unit stuff. The tensor unit just means the thing like trivial representation in rep G, which when you tensor it with anything, doesn't change it. Okay, and so this is a good example of a fusion category in the sense that it is not going to be commutative in general. So if G is non-abelian, then that means that there's some little g and some little h, such that little g doesn't equal little g, little h times hg aren't the same. And so that means that E of these things aren't the same, or if you prefer, C or whatever I called it, these things aren't the same, which means C of G tensor C of H is not the same and not equivalent to C of H tensor C of G. That's provided GH isn't the same as HG in the group. So as I said, fusion categories don't have to have this property. Rep G does. So in that way, Rep G is a bad example of a fusion category. It has an extra property that's pretty special. And so these examples don't have that extra property. Okay. But that's what you should think about. So when you're thinking about a fusion category and you've forgotten what the real definition is, just hold in your head these two examples, G-graded vector spaces and Rep G. And for the most part, you'll get an idea. you can apply whatever theorem you're seeing to those examples, and you'll get some idea of what the theorem is saying. These are still extraordinarily special fusion categories, but they're kind of prototypical in that sense. That's what fusion categories look like. Okay, well, at some point we have to address the question, when are two fusion categories the same? When should we regard them as the same? And so the obvious definition, the definition I would have come up with is that there exist functors in one direction and functors in the other direction. Functors are just the obvious generalization of functions to categories. So they're structure preserving, and they move objects as well as morphisms. And so you have your two functors. You have the functors going in both directions, and they're inverses of each other. So the composition in both directions are the identities. And of course, they have to preserve all the structure that's present. So for fusion categories, they have to respect tensor products and sums and duals. But this actually is pretty strong. It's a little bit too strong, because we often have different ways to describe the same thing, and we're a little bit sloppy on exactly what we mean. So for example, I said, think of rep G for concreteness as matrix representations. So this is a bit of a unsophisticated way to think about representations. You can also think of them as G modules on or vector spaces or whatever. But it's the same thing. So it's morally the same, but it actually is different. So it's not true to say that Cn are the only finite dimensional vector spaces, but they are. So that's an okay thing to say, but you're actually committing a wrongness. And so, but that's a pretty silly way to be distracted. And so if your definition of equivalence of categories distinguishes those two things, then you're going to end up having any theorem you have are going to have lots and lots of you're never going to get uniqueness. You're going to have this thing determines this category, modulo all of this fudginess of being really careful of what you mean by a vector space, for example. Anyways, that's not the way that we're going to define, the way we're going to identify categories. The way we're going to identify categories is the equivalence definition that I give at the bottom of that slide. And so what we require is that it's a morphism, it's an isomorphism at the level of Hom spaces when it's defined. So when you have, so your functor goes from C to D, and so for any object C and C prime in the first category, I know what FC is and what FC prime is, and those Hom spaces have to be isomorphic to each other as vector spaces. And so that's the same as it would have been up there. The difference is in the second condition. We don't require that it be surjective. So we don't require that all of the. So all we require is that. So I might not get D spot on. My functor F might never land on D spot on, but it'll land on something that's isomorphic to D. So that's good enough. And so that's what equivalence means. So all of our definitions are going to be modulo this notion of equivalence of categories. This is standard. So if it's completely new to you, then you'll see it in action. Lots of places. Okay, so one of the things that we need to discuss is how to enhance VecG. And this is a gift given to us by categorification, a gift given to us by this enhancing idea. So a group is a pretty rigid object. There's not much we can do to gently tweak a group. But there are things we can do to gently tweak a fusion category. And so let's look at VecG. So these again are these G-graded vector spaces. It's not far off just the vector space of all, the category of all vector spaces. It's slightly enhanced. And so associativity here, as we know, associativity is the key building block of these fusion categories. What it has to consist of is these linear maps from, so for semi-simple categories, it reduces down to understanding what's happening at the level of the simples. So once you understand what's happening at the level of simples, then everything else gets given to you by free. A non-simple, a generic object will be a sum of simples, and its associativity isomorphisms will come for free from those of the building blocks. So we just have to deal with finitely many building blocks. So the world of fusion categories is vastly simpler for that reason. So all we have to understand are the associativity isomorphisms for the simple objects. And we know what CG, tensor CH, tensor CK is, no matter where you put your brackets. What this is CGHK, which is another simple object. So this is a very special category where the product of two simples is simple. And so what we have, our associativity isomorphisms go between simples. And so by that Schur's lemma formula, that's a one-by-one matrix. So it's a number. So these associativity isomorphisms are just non-zero numbers. They have to be isomorphisms. They have to be invertible. So they're just non-zero complex numbers. Now, in vec G, we make a choice. These associativity isomorphisms are the obvious things. That number, which do I call it? I think I call it big A, is just the number 1. It has to be a non-zero complex number, and we just take it to be the number 1. But why? We have a freedom to make it anything. We can make it pi if we want. Well, we can't make them all pi because we have the pentagon identity to satisfy. So in this context, the pentagon identity comes down to that. But we can make any choice of complex, non-zero complex numbers, capital A's, such that that pentagon identity is satisfied. So there's lots and lots. There's infinitely many different choices to make. And so we get a different fusion category for any omega satisfying that relation. So you might recognize that relation. Those kinds of relations that look like that are cocycles. That's a 3 cocycle. Okay, well, who cares? Actually, it's kind of important. So we have lots and lots of ways to twist a category. So for any choice of capital A's that satisfy the pentagon identity, we get a different, potentially different category. And so we're going to call it, I'm calling it vect omega in anticipation of what's on the next slide. But I should have called it vec capital A or vec whatever. Okay, there's lots of different things, but remember what the previous slide talked about. It talked about different ways to think about a category. When are two categories equivalent to each other? And so we don't care if you twist something into a new form, but it's equivalent to the old form. It's just looking at it in a different basis or something. Then that's not very interesting. So you want to mod out by those kinds of things. And it's very easy to specify what's going on there. And that's given by, well, I try to explain it in that slide there. So I'm just copying down the definition of equivalence of fusion categories into the language of this very easy, very friendly tensor category, vec G. And so, so this functor, it lives at the level of objects where it's clear what's going on. It's going to send CG to CG. But what's more exciting is what it does to morphisms. And there you have the flexibility. You don't have flexibility at the level of objects, but you have flexibility at the level of morphisms. And so you have wiggle room. And so your wiggle room for your functor is it has to be an invertible number. Again, it's 1 by 1. So these mu's, I'm calling them mu's, they have to be non-zero complex numbers. But otherwise, they're completely arbitrary. And so if you track down what the omegas, so these, what I'm calling omega, I've switched notation here conveniently. So omega of G, H, K is equal to what I had called A, G, H, K, I think, on the previous slide, just because this is a more standard notation. So these omegas defined in this way satisfy the 3 cocycle condition if you satisfied the pentagon, which you have to. And you want to mod out by these mu's. Well, the result is precisely H3, the cohomology group H3. If you don't know group cohomology, that's okay. Just treat it as a black box. But this is vital for VOA, the world of VOAs. This flexibility here, you see all the time. So this is not just some abstract nonsense thing. Actually, it is completely abstract nonsense, but it appears blatantly in the VOA land. I think that means I'm speaking too much. Okay, and so more generally, this is just a baby example of this, but more generally, anytime you have a fusion category, and you have a grading on your fusion category by some group G, then you can twist the associativity isomorphisms in exactly the same way by H3 of that G. So anytime you have a grading. So for example, rep G, a pretty boring category, I'm pretty sure you feel like. So one charm about rep G versus vec G is that not all of the simples are invertible here. So you get two-dimensional representations of G, or five-dimensional, or 196,883 dimensional. But so in that way, it's better than vec G, or more typical than vec G. On the other hand, it's commutative, unlike vec G. So anyways, who cares? Rep G, it turns out this has a grading on it. Does anyone know what the grading on rep G is? How can you grade representations? So grading just means that you the tensor product, it respects tensor product. So if the grading of this thing is even and this thing is odd, then the grading of the tensor product better be odd. That kind of a thing. Does anyone know the grading on rep G? We all know rep G. We've known about reps of finite groups for, I don't know, decades or longer. What's a grading on this category? Well, it's graded by 1, for one thing. But that's not so interesting. Is there a slightly more interesting thing? Okay, it's graded by the center of G. So that means that you can twist rep G by any cocycle in this. So, so the center of a group is usually pretty small for typical groups, but it's often non-trivial, and so you can twist a very, very, very familiar object by a very, very, very familiar beast, H3 of an abelian group. And so you can think about it as a little exercise if you want. You can think about what it looks like. So what classical, how do you describe that? Okay, right. So you can, so as I say, anytime you have a fusion category graded by a group, you can twist it in this way. So it's a free way to create new fusion categories. Sort of a cheap way, but so the fusion categories, so our symbol for this twisted vec G is vec G omega, where omega is your 3 cocycle, and these are generally very different from vec G's. So you've moved into new categories, new category land. So there's a precise statement that these are inequivalentist categories if and only if. So the only time you have equivalence, and these things are equivalent to each other, is when, so this is equivalent as a tensor category, as a fusion category, if and only if, so this is equivalent to H omega prime, if and only if G is the same as H, and omega is the same as omega prime, modulo automorphism. An automorphism of G. And as you know, as you may know, inner automorphisms don't change your 3 cocycles, so really you're talking about outer automorphisms of G. So up to outer automorphisms of G, these things are always inequivalent to each other. So it's a real way to create new categories. Okay, so I have a bit of time left. So let's move on to the connection to VOAs. And so for most of my lectures, maybe for most of my lectures, I'm going to restrict to rational VOAs or strongly rational or completely rational or whatever. So these have all the nice properties like C2 cofiniteness and whatever else. So maybe on a future slide I'll spell this out explicitly. But so there's things you can say, very interesting things you can say when you drop these conditions. But the happiest, friendliest situations are when you have a rational VOA. So that's the situation to start with, at least, and then you move on from there. So there's lots of examples of such things. For example, lattices. When you have a lattice, you get a VOA, and these are going to be strongly rational in this sense. A very rich source of these things come from Lie algebras. So an affine Lie algebra, VOA, is I'm not going to define what these things are, but again, you can just treat these as black boxes, but I'll use them in my examples. And so you get a nice, friendly VOA every time you have a semi-simple algebra and a positive integer, which is a positive integer k. Then you get a VOA and with all these nice properties, a strongly rational thing. Virasoro mineral models, et cetera, the moonshine module, all this kind of stuff. And so in foundational work, Yichi, who will be coming here today, later today he'll be giving his first talk, he's characterized the representation theory, and what he's found is that the category of modules of V, so the objects are modules of V, defined in a certain way that maybe we'll spell out explicitly later, or maybe we won't. So it's just the obvious notion of module for a VOA. They form a fusion category. So the category of modules is the objects are the modules, and intertwiners are the morphisms, and you get a tensor product in this case, et cetera, duals, you get a fusion category. But actually it's much more. So it comes with a braiding, so it commutes. We'll talk more about this later. And so it's more like rep G than it is like vec G in the sense that it is commutative, it is braided. But that's where the similarities end. Rep G has a braiding, has a commutativity that's as degenerate as possible. And the category of modules of a VOA has a commutativity isomorphisms that are as non-degenerate as possible, the other extreme. And this makes all kinds of difference. So the result is not a mere fusion category or a braided fusion category, but a modular tensor category. So we're going to talk more about that in the next few slides. So we know that a fusion category we can think of as a categorification of a ring. I'm not sure if I ever talked about what a fusion ring, oh maybe I did. Anyways, a fusion ring is just the combinatorial shadow of these tensor products. So xi tensor xj is isomorphic to a sum of xk's. So that's the fusion ring. You get a product. The equivalence classes are your basis elements in this ring, et cetera, et cetera. So a fusion category is the categorification of this, so lifting it up one categorical level. What's the categorification of a commutative ring, on the other hand? Well, of course, you're going to have an extra relation in there. You're going to have x times y equals y times x. But we know, because we're very knowledgeable 21st century people, that we should feel anxious when we write down equality of objects. So what we really mean is to spell out, specify the isomorphism between these. Think of this as an equivalence of tensoring two representations, for example. And we want to identify what that isomorphism is. And choosing a different isomorphism, like we did by twisting vec G. We just tweaked these isomorphisms, isomorphisms, and in a trivial way by just multiplying them by numbers, and we got different fusion categories. So we have to spell out what these braidings are. And once again, so what we need are, so the extra data that'll come in if you have a commutative fusion category, or more precisely a braided fusion category, you'll need to spell out what these commutativity isomorphisms are. They're called braidings. And once again, you'll have the same kind of coherence issues that you had before. So because we want these isomorphisms to always be unique, whenever we write down something like x tensor y tensor z equals z tensor y tensor x, and we change we put brackets in however you want. And we don't have to stop at 3 equals 3. We can have 67 equals 67, where we just rearrange their orders. Then there's going to be different ways, usually, to go from here to here. By using commutativity at some point, using associativity at some point, and if it's complicated enough, you'll use lots of commutativities and lots of associativities. You can be terribly inefficient if you want, and use commutativities and anyways, no matter how you do it, you want to get the same answer. So you want to have coherence again. So the diagrams of, I guess we could call them generalized commutativity, associativity should commute. The different combinations of bradings and associativity isomorphisms that you get from taking different paths from here to here should always agree. When you compose them all together, they look different, but they have to agree to each other. And so, once again, it's been sorted out what this means. You don't need to check infinitely many different conditions. It reduces down to one or two, the pentagon identities. And so there's some simple identities that you have to check that I think come from this thing here. And that gives you, if that's satisfied, then you'll have coherence for commutativity and associativity. You also have to worry about duals and tensor units and stuff, but that's all routine stuff. I'm going to ignore it. So that's what a braiding is. So braiding has to satisfy, just like associativity had to satisfy the pentagon, here you have to satisfy the hexagon. I think is how it goes. Okay. Now, it's called a braiding because if you have a braided fusion category, then on each of these Hom spaces from x to x, or endomorphism of x, that just means Hom of x, comma x. And we can take lots of copies of it. So I'm going to write it as n times x. So it just means x plus x plus x plus x n times. So there's a representation of the braid group Bn on this thing here. So that's where the word braiding comes from. Now, so that's the case, for example, for rep G. Rep G is a braided fusion category, and you're going to get representation of the braiding on this. But in fact, much more is clear. So in the case of the braiding of G, you have what's called a symmetric braiding. So you have this composition that is the identity. So if you twist things like this, and then you twist them back again, you get back the same thing exactly, spot on. It's the identity. And so this is called, so in this case, this action, the braid group action collapses to or projects to, quotients to an action of the symmetric group. So this is a quotient of the braid group by the pure group. And so the representation, so this thing, in this case, for example, it quotients to this. And in fact, the same thing happens for any symmetric fusion category. And so, so that's why these are called symmetric fusion categories. So they're the boring case. They're the extremely degenerate case. So we're interested in the exact opposite. So, so here's some examples of braided fusion categories, and some non-examples, like, for example, vec G, when your group isn't abelian. So obviously, so most fusion categories are not going to have any chance to be braided because their fusion ring must be commutative to be braided. So you must have x times y being isomorphic to y times x always, or you have no chance to be braided. And so vec G, for example, usually doesn't have that property. Okay, so now to define a modular tensor category. So these are the category of representations of a nice VOA. What we can do is define a matrix, an S matrix. So this involves the categorical notion of a trace, and I'm not going to get into that definition. But what you do to find out how to define trace. So we all know what trace means. Trace means you sum up the diagonal elements of your matrix. But you can interpret this abstractly. You can interpret this in the category vec without talking about take the I entries of your matrix. What does that mean? And so you can build that up by using the ingredients in your fusion category, and you can define traces. And so I'm not going to spell out that, but it's an interesting exercise. And you also will require a pivotal structure. Pivotal structure means a choice of isomorphism of the double dual to X. Okay, but let's just ignore trace. Let's pretend that we know what trace means. And so what you do is you take your braiding x, y, and you compose it with the braiding yx. So this thing goes from x tensor y to y tensor x. And so to compose it with this thing's going to go from y tensor x to x tensor y. So composing it gives us something. This thing here is going to be an element of, it's going to be a truly square matrix. So you get a well-defined notion of a trace there. If you change the columns, you're going to also change the rows. And so, so we're composing like this to get something that's in an end of something. And then we're allowed to take the trace of this, it turns out. And the trace of this combination, as I wrote up there, is the S matrix. As I mentioned up there, traces, it's a categorical notion. You have to spell it out in categorical terms. And what that means is, so all the general properties like conjugation, the cyclicity property of trace still holds. But numerically, there's some surprises. So if you take the trace of the identity matrix, so the trace of the identity matrix is just the dimension of your vector space. Well, the exact same thing happens in your category. The trace of the identity and the identity endomorphism on your object X is just the dimension of your object X. But dimension, in general, is not an element of the positive integers. It doesn't even have to be positive. So it'll be, can be very strange looking, very irrational numbers. So dimension means it in a fractal sense, sort of. So you'll get algebraic numbers out, but so you have to be so. Right. Another thing is there's different meanings of the word of the symbol S, and I'm sloppy in these notes with it. So this is what I would call S Hopflink. So not infinity, but Hopflink. So in these braided fusion categories, you get representations of you get knot invariance, link invariance, ribbon invariance, in fact. And so the ribbon, this thing here, it turns out, is going to coincide with the invariant for the hop link that comes from your category. Anyways, who cares? It's not important to us. We have this abstract, who knows what good this matrix S is. Maybe we'll find a use for it someday, but at least it's used in the definition of modular tensor category. The S matrix is a very important combinatorial invariant, as we'll see. Right, so as I write up there, I'm sure the definition of a modular tensor category is that it be as not S is invertible. So if we were to compute this thing, okay, I write it out here. If you can compute this, so we know, let's look at rep G, that's the more interesting one. So rep G, we know what the braiding looks like. It just flips EI tensor EJ prime with EJ prime tensor EI. And so when you compose that with its reverse, it's the identity matrix. So it's the identity linear map. It sends EI tensor EJ prime to itself. And so, so what we have to do is take the trace. So in this case, as for any symmetric tensor category, we take the trace of the identity map on rho tensor rho prime. So this is going to be the S matrix entry for this. And the trace here is in the normal classical sense because this is a very classical category. And so this is the dimension in the normal boring sense of rho tensor rho prime, which means it's the dimension of rho tensor the dimension of rho prime. So that's what the S matrix looks like. It decomposes it into a product like this. And so we run over, it's a finite by finite matrix. In particular, we run over all rows and rho primes that are simples. So for S3, for example, our matrix would be, the S3 S matrix is going to be, the rep S3 S matrix is going to be 1, 1, 2, 1, 1, 2, 1, 1, 2, 2, 2, 4. Does anyone know the determinant of this matrix? That's right, it's 0. What about this? What's the rank of this matrix? There's only one vector of information that goes into this. If you know that vector of information, namely the dimension of all of the simples, then you know every element of this matrix. This is a rank 1 matrix. So it's very, except in the stupid one-dimensional case, this is invertible. This is non-invertible in the strongest sense possible. Its rank is as small as it can possibly be. So that's the case for any of these. So this is not modular. So this is as far from modular as possible. It's braided, but it's not at all a modular tensor category. So it's not interesting directly to the category of modules of a VOA. But if examples of modular tensor categories are, so what happens, well, I spell out an example. I think we're all getting kind of tired, so I'll speed this up. There are ways to get categories of, there is a possibility to get modular tensor categories. One example is associated to an abelian group G. So you can, it's a braiding that you can put on vec G, a different braiding that you can put on vec G that gives you a modular tensor category. And it comes from a bilinear form, a non-degenerate bilinear form. And so this is where you see this. I'll talk about this more later, but you'll see this in the lattice VOAs, for example. And so modular data is, so just like the combinatorial basis, the main shadow cast by a fusion category is the fusion ring. The analog for a modular tensor category is the modular data. So this is the S matrix that we've just seen. And there's also a T matrix. The T matrix corresponds to the invariant that you get from a ribbon. So you actually do this. Or maybe it's the other way around. I don't remember. This way or it's mirror image. Every time you have a ribbon, linked ribbons, so this is a pretty boring ribbon. This one, the numerical invariant that you get for this, for each choice of a simple object here, you label your ribbon with a simple object V, then that's going to be the twist. Or maybe it's the complex conjugate of the twist, depending on if I've done this properly or not. And this is your T matrix. So you get a matrix T. So T matrix is a diagonal matrix with the twists on the diagonal. And the S matrix is another matrix. I'll write down these for some interesting examples. And this, it gives you a representation, at least if you tweak it slightly, you get a representation of the modular group SL2Z. That's where modular tensor category comes from. And you also get a description of the fusion ring. A modular tensor category is a fusion category if you forget the braiding. So you get a fusion ring, and the fusion ring is completely determined by S. S is like the character table of a modular tensor category. That's how you should think of S. And so the combinatorics of the modular tensor category is through the modular data primarily. So we'll see more about the modular data later. So what you get when you have a modular tensor category is you get braid group representations, of course. You get knotted linked ribbon invariants in any three-dimensional manifold. You also get projective mapping class group reps in every genus. For example, the mapping class group, SL2Z is a mapping class group of the torus, the punctured torus, one punctured torus. So you get a representation of SL2Z and lots of other things. So towers of, doubly infinite towers of mapping class group representations. So how to build your own modular tensor category. So it sounds like modular tensor categories are a little bit more important to VOAs than fusion categories are. One way to build a modular tensor category that'll turn out to be important for us is it's a simple idea that comes from the picture of categorification. So we're supposed to think of, at least sometimes, of a fusion category as the categorification of a ring, the fusion ring. So we know that modular tensor categories is the categorification of a commutative ring. And so is there some way that we get a commutative ring from an ordinary boring ring, some generic way? And if so, can we categorifize it? Can we interpret it categorically? Well, there's an obvious way to get a commutative ring from a generic ring, and that's just to take the center of the commutative ring. So you look at all of the things in your ring which commute, all the things little r in your ring, big R, which commute with everything else in the ring, big R. And so we're supposed to categorize this, and we should feel, by now surely, you all feel nervous when I wrote down R prime equals R prime R, because that's equality at the level of objects. And so you should feel anxious. You should be sweating at this point until it's corrected. And what you have to do is you have to say which isomorphism, you have to pick an isomorphism that sends you from R tensor R prime to R prime tensor R. And so you spell all this out, interpret it categorically, and what you end up with is the center construction of a modular tensor category from a generic fusion category. So given any modular tensor category, you can create a modular tensor category, so a non-degenerate beast, not just braided, not just commutative, but non-degenerately braided, from this center construction. It's a very simple construction, at least conceptually, but it isn't fun to do in practice. Unfortunately, we're going to have to do this. We're going to have to do a little bit of work in our next class, our next lecture. Okay. Well, we're running out of time, so we'll come back to this a little while. But you can see what the answer is going to be. So if we try to do this for vec G, what are the objects of your center going to be? They have to commute with everything in your group G. And if G is not abelian, well, they don't commute. So what can you do? Well, actually, there is a center of the group ring, and it's spanned by the conjugacy classes. So the object part of the objects of your center of the fusion ring of vec G is going to consist of conjugacy classes. So that's how you're going to have a chance to get commutativity, and then we're going to have to talk about the second component of the object in the center. It'll be some representation of a centralizer, but we'll worry about that next class. But that's what the center is looking like. So, okay, so if we have so I could have given this slide a little bit earlier, I guess, but let's suppose we have, just to spell out what these things look like for modular tensor, what a modular tensor category looks like for a VOA. So if we have a nice VOA, so a nice VOA for me will always mean just completely rational. So all of the assumptions that go into Huang's theorem. So if you have a nice VOA, then you have a category of modules, which is a modular tensor category. So if M is a simple module, then, well, your VOA comes, these VOAs come with a copy of the Chiral algebra. And L0 is part of the carton subalgebra, if you want, of this Chiral algebra. You can diagonalize it in all of the representations. And so we write down the eigenspace decomposition of our module M, the one that corresponds to L0. So in physics language, L0 is the energy. So the ground state of this module would be energy H, where H is some rational number. And so it turns out that the twist of this is going to be the exponential of this H, HM. It's called the conformal weight. We also have, so we have the graded dimension, or what some people erroneously call the character of our module M. It's just the sum of the graded dimensions, the dimensions of our module. And there's this weird q to the whatever factor in front that is just made for the sentence coming up. So you have to adjust all these things a little bit in order to get true representations of SL2Z, in order to get vector valued modular forms. And so it turns out these graded dimensions form a vector valued modular form for SL2Z, where the multiplier is our modular data. I'll talk more about this a little bit later. So the VOA sees pretty directly, you can see pretty directly a lot of the data of your modular tensor category, certainly the combinatorial parts you can see. Okay, so quick examples. Well, the easiest example, as always, are the lattice VOAs. So you take your favorite even positive definite lattice L. L star means the dual of it, so all of the vectors in the realification, the ambient vector space that have integer dot product with everything in your lattice. So that's going to be a bigger lattice. It's going to contain L as a sublattice. as a finite index sublattice. And so take the quotient and call that G. And then G and the dot product that you get on G gives you the modular data directly. So I've normalized S the way I want to, but I forgot to normalize T the way that I want to. So I want to have a slight fudge factor added to T, but let's just ignore it. A much more interesting example are the affine algebra VOAs. And so for the easiest case, affine A1, the simples are you can think of them as the numbers from 1 to k plus 1. The S matrix is a bunch of signs. I forgot a bracket there, but that's all that I forgot. And then we get the T matrix is a bunch of other roots of unity. And so more generally, the simples are parameterized by the level k highest weights. In this case, they're shifted by the Weyl vector rho, which is 1, which is why I'm going from 0, when I'm going 1 to k plus 1. 0, or 1 in this case, will be the tensor unit. S is the numerator of the Weyl character formula, and it's alternating sum over the Weyl group, which is sim2 here for A2, A3 it'll be sim3, et cetera, et cetera. And T is the second Casimir of the Lie algebra exponentiated. So the modular data knows everything about the Lie theory, and every question you can ever ask about the modular tensor category corresponding to affine algebra VOAs, if you look at it properly, has a beautiful Lie theoretic answer. We'll talk about these a little bit later. And that's truly time for me to quit. So maybe this is a good time to quit. So I'm actually at the first interesting point of my talk. So this is probably a very good time to stop. And so next class will begin with a bang. So this class was just, it turned out just review of stuff, a very quick review if you haven't seen it before, a very long, slow review if you have. But starting next lecture, I'm going to tell you about why, if you care about VOAs in the slightest, why you have to use tensor category methods. And so that'll start on my next lecture, but until then, are there any questions?
Any questions?
I'm around all week, next week as well, so you can come and stop by and talk to me. Buy me a beer and talk to me. Buy me a beer and don't talk to me.
Hi. Over here.
Oh, sorry.
Is there a group cohomology interpretation of the twisted braidings on vect G that you explained?
Is there a
like a classification?
Yeah. So the twisted. So they're classified by H3, G, CX, and you really should quotient by automorphism. And so that is the classification, the bijective classification of all possible twisted braidings on braidings. Period. Twisted or whatever. However, these are the classification of all possible braidings on vec G. So
sorry, how did that differ from the associators that you were talking about?
Oh, twistings. So this
I was saying
is
braidings.
So the braidings on. I see. Sorry, I misread your question. Right. So if we just have ordinary boring vec G, then in order to have braidings, we'd have to have G be a commutative. It'd have to be an abelian group for one thing.
Yeah, sure.
And then the classification of all possible braidings on vec G, let's call it A, just to remind ourselves that it's an abelian group. So the possible braidings on vec G are given by, there is a cohomological interpretation, but the easiest interpretation, so there is one, but these are abelian cocycles is the way that it's described. But in my opinion, the easiest description is in terms of quadratic forms. So a quadratic form on an abelian group is a map from your abelian group to, actually it's exactly what it sort of sounds like. So it's a map from here to
I think you said, like, you called it a bicharacter or something like that.
Yeah, so it's more than a bicharacter. It's kind of like the square root of a bicharacter. But yeah, so it has the property that when I take A plus V, then I get Q. So you just think, so I might write this down wrong, but this is embarrassing if I do. And you get some kind of another beast. The middle term here is a non-degenerate bicharacter. So it's kind of this, or maybe I have to square something. Shit, I think this is right. So this is a bicharacter on A, B. So a quadratic form means that when I define B by this formula, so in other words, I put a complex conjugate on these things because these are going to be in the unit circle. I may as well make them in the unit circle. And so then this thing is equal to B. Then this has to be a bilinear form. And so this is just a bilinear form. So for example, for Zn, this is the answer for Zn. So for Zn, the possible non-degenerate bilinear forms are, so the bilinear form on AB is going to equal e to the 2 pi I AB over the order of the group times some m, which is co-prime to n. So there's some really simple description of all bilinear forms. And with quadratic forms, which is really what, so B is what tells you the S matrix directly. The quadratic form tells you the T matrix. And so there's usually a square root difference between T and S, it turns out. And so, but anyways, so the details I'm not going to get completely right now. We can talk about it later, or I can reference you. For example, the book by Eddinghoff, the book called Tensor Categories by Eddinghoff and everyone else, has a chapter, a section on it, a long section, which describes the cohomological parametrization of all of the modular tensor categories, all of the twists that are possible on vect A, and also this interpretation here. So it gives you both interpretations and the map between them. So it's the most complete description of this part of the story that I know. So you can look at it in the book there. And if you can't find it, then just ask me.
Thanks.
Other questions? Questions from the Zoom audience?
So VOAs, of course, see all of this. So VOAs see all of these different twists. They see all the different associativity twists. In fact, VOAs know everything about tensor categories.
Okay, so if there's no other questions, let's thank the speaker again. So I guess now is lunchtime. I mean, it's only 11:30, but we return at 1 o'clock after lunch. Lunch is in the cafeteria downstairs. Yeah, I think that's it.
Yeah, I'm around. I'll be around also.
Something about this
Sure.
category version of the same thing.
Okay, sure.